Welcome everyone to our webinar, Managing the Challenges and Opportunities of Atmospheric Rivers. My name is Hunter Johnson. I work at Upstream Tech on our HydroForecast product. I have a background in hydrology, water resources engineering, and I'm a customer success manager. And I'm joined today by Nathan Baskett, who's a hydrogeologist at Sonoma Water, and he works on the water resource planning team. And a high-level overview of what we'll be discussing today. Nathan will be diving into what is Sonoma Water, what are they doing, and a lot of the interesting challenges and details that the agency is facing and tasked to operate under. I'll talk a little bit about what an atmospheric river is and what some of the challenges of understanding and forecasting those types of weather events are. Then Nathan will talk about kind of those 2 points overlapped of what is some of the research about atmospheric rivers happening in Sonoma and what are the impacts of atmospheric rivers on Sonoma. Then I'll go into Upstream Tech's hydrology forecast product called HydroForecast and how that's being used and some of the benefits that that type of technology can offer people like Nathan. And then we have a case study of a recent atmospheric river in November 2024, where I'll walk through information that was being forecasted and how the HydroForecast product was showing increases in reservoir inflows. So I'll pass it over to Nathan to talk a little bit about Sonoma Water.
All right, thanks, Hunter. Yeah, so Sonoma Water, it was created as a special district by the California legislature in 1949 to provide water supply and flood protection. It currently serves as a wholesale water supplier to about 600,000 residents in both Sonoma and Marin counties. Next slide, please. So the Russian River acts as the primary source for water supply, which is fed by two reservoirs. You have Lake Mendocino near Ukiah in the northern part of the watershed, which discharges water into the upper Russian River. Lake Sonoma and Sonoma County discharge water to Dry Creek, where it meets the Russian River just downstream of Hillsburg. And then water is then diverted out of our transmission system using collector wells adjacent to the Russian River. Sonoma Water also has supplemental groundwater wells in Santa Rosa Plain, which are primarily used during droughts. In addition to water supply, Sonoma Water also provides flood control by maintaining 80 miles of streams throughout the county. And we also, starting in 1995, we assumed management of 8 county sanitation districts. Next slide, please. Okay, so Lake Mendocino and Lake Sonoma, they are multi-purpose reservoirs. They provide both flood protection and water supply. So Sonoma Water is responsible for flood water supply in the reservoirs, while the U.S. Army Corps of Engineers are responsible for flood protection. Here's a hydrograph of Lake Mendocino for water year 2024. The blue shaded area is considered water supply pool. Anything outside the blue shaded area is considered the flood control pool. As you can see, during the winter, when flooding is a concern, the water supply pool shrinks and the flood control pool expands. Anytime storage is within the blue water supply pool, Sonoma oversees releases from the reservoir for water supply purposes and to meet minimum in-stream flow requirements. Anytime storage is outside of the water supply pool, the Army Corps is in control of reservoir releases for flood control reasons. Next slide, please. So being how our wet season lasts only a few months, our area is very vulnerable to both prolonged droughts and flooding, which requires careful management of our water resources. Recently, California experienced extreme drought conditions between 2019 and 2022. Rainfall dropped well below average statewide, which had major impacts on water supply conditions here in Sonoma County. In fact, Lake Sonoma reached its lowest storage ever recorded since its construction in 1984, with storage dipping below 100,000 acre feet for the first time. When we are not experiencing droughts, we also have to deal with flooding, which normally come in the forms of atmospheric rivers, which has caused over about $5 billion in flood damage locally over the last 40 years. To talk more about atmospheric rivers, I'm going to pass it over to Hunter.
Yeah, thanks, Nathan. So we have a pretty wide variety of folks in the audience. So I'm gonna go over some of the basics of atmospheric rivers, and I understand some people may be very familiar or more familiar than me with this. And yeah, to better understand what some of the people in the audience are experienced with atmospheric rivers, we have a little poll question, so you can answer that um, whenever you get a moment. So to zoom out and talk about on a high level what an atmospheric river is, it's a thin band of water vapor that is transporting water vapor from the tropics to one of the poles. And it very literally looks like a river in the sky. So these are very long, thin ribbon-like plumes of moisture that are transporting massive amounts of water. And some interesting stats that scientists have found is that the mean flow or the amount of water vapor in a typical atmospheric river is about 7.5 to 15 times the mean flow at the mouth of the Mississippi River. So quite literally, these are rivers in the sky. And with that in mind, they're very, very large rivers with a lot of water. And looking specifically at California, the frequency and severity of atmospheric rivers are vital in terms of if it's going to be a dry or wet season. So if there's not a lot of atmospheric rivers, it's very likely that's going to be a drought after that winter. And if there are several or very extreme atmospheric rivers, it's going to most likely be a very wet period of time. And during this presentation, obviously, Nathan is based in California, so we'll really be focusing on California and atmospheric rivers. I do want to highlight that what we're talking about is a global phenomenon and is very generalizable. So with atmospheric rivers, they happen all around the world. And so they're happening in Western Europe, they're happening in South America, Africa, Australia, and Asia. And it's, although it's happening in different places, it's still the same concept of this really thin ribbon of warm atmospheric water vapor from the tropics being transported towards a pole, and that being a very large amount of water. And then I also will say that a lot of the ideas and principles we're talking about can also be extrapolated to non-atmospheric river, but extreme precipitation events. So things like cloudbursts or hurricanes. So even if you're areas that don't really experience atmospheric rivers, there's still lessons and things that can be transferred over from what Nathan and I are going to be discussing. Atmospheric rivers are in the news all the time. Just a couple of months ago in the US Midwest, there was quite a severe atmospheric river, which caused some very severe flooding and pretty extensive damage. So even in places that aren't typically known for atmospheric rivers, they still experience atmospheric rivers. And then kind of looking under the hood of what exactly an atmospheric river is and thinking more importantly about how do we forecast and understand what's going to be happening in the near future with atmospheric rivers. The really important aspects of being able to forecast them comes from their internal geometry. And I'm not a meteorologist, but it's the structure is the most important part to understand the direction and also how intense or severe that precipitation event is going to be when that water gets over land. And since these events are occurring, they originate in the ocean. There's not a ton of sensors in the ocean. So the amount of data on the ground or in the ocean to be able to understand the structure of the atmospheric river, and then what is traditionally used in meteorology from satellite data, those two traditional forms of data for forecasting aren't super impactful in terms of highly specified forecasts because there's a sparse amount of the ocean sensors and the internal structures obscured. The internal structure is obscured by the top of the cloud. Fortunately, there's been some really amazing research into solving this really tough problem from researchers specifically at UC San Diego, where they have increased the amount of ocean sensors. They fly planes over atmospheric rivers and drop sensors to understand their internal structure. So they have really sophisticated methods to be able to understand what's happening in the ocean and where it's going to be moving. And one thing I want to point out is because atmospheric rivers are so small and they kind of wave up and down like a hose, if that forecast changes just a little bit, the impact of the water manager like Nathan waiting to understand if they should hold or release water, that the change of the exact impact location can have really profound impacts on decisions that are being made 1 or 2 days in advance of the atmospheric river. And I want to talk about a really interesting case study, specifically of atmospheric rivers in California, that gives some insight of the uncertainty and challenges of forecasting, but also talks about how precipitation forecast is a critical part of the puzzle, but isn't the entire part of the puzzle. So in 2017, Lake Oroville, which is one of the main reservoirs in the California Sierra Nevada, experienced several back-to-back atmospheric rivers. And in February, at the end, after about 4 or 5 atmospheric rivers, a very intense atmospheric river occurred that dropped about 9 inches of precipitation over the basin. And the inflow of this reservoir increased by about 6 times. The emergency spillway was activated, which is what this photo is. And the water levels got to the very top of this dam and caused emergency managers to evacuate 200,000 people or so downstream of that dam, just in case there was a failure. As I was looking into this case study, the thing that was really interesting to me is that the atmospheric river precipitation forecasts were actually quite accurate. So water managers and folks in this area understood a lot of rain, or I should say precipitation was coming towards them, and they understood there was a sequence of events too. But the challenge was how that rain was going to fall, where it was going to fall, what it was going to do to the existing snowpack and the antecedent conditions, so the hydrological modeling aspect of it. So this photo shows before the series of atmospheric rivers, and then after, and what the snowpack impact was in the watershed of Lake Oroville. So as you can see on the left, there was a lot of snow. It was a very wet, very dense snowpack year. And after that last atmospheric river, it was a very warm, primarily rain, water precipitation event. So all that snow got washed off as a rain on snow event. So even though the water managers and folks in the area understood that a lot of precipitation was coming, they didn't fully understand that it was going to cause a snow event. And sorry, I'm having can you hear me, Nathan?
Yep.
Sorry,
We can still hear you.
my headphones just died on me. But yeah, to finish my thought, they weren't fully aware of the hydrological impacts of that rain on snow event and the massive amount of inflow that was going to come as a result from that precipitation. So I'm going to pass it back over to Nathan to talk a little bit more specifically about Sonoma's research with atmospheric rivers. And actually, Nathan, before I do that, I forgot to say at the top, if you have any questions, please drop them in the Q&A. And at the end of our discussion, we'll go back and we can answer that and have a bit of a discussion. But over to you, Nathan.
Great. Thanks, Hunter. So unlike Lake Oroville watershed, significant snowfall does not accumulate in our region. So all the water that enters our watershed and reservoirs usually comes as runoff during or immediately after a storm event. About half of our cumulative rainfall comes during an AR event, which brings a lot of rainfall in a short amount of time. About 60% of all drought busters have come in the form of an AR. So they're incredibly important to our water supplies. However, ARs, they also cause about 87% floods in our region over the last 60 years. So here are some examples of some notable floods. In 95, there was thousands of residents had to evacuate Guerneville when stage reached 45 feet, which is 11 feet above the flood stage. The flood of record occurred in 86 when the stage in Guerneville reached nearly 50 feet. More recently, in 2019, major flooding occurred again on the lower Russian River, causing millions of dollars in damage. But also this last flooding event in 2019, it happened right before we entered a 3-year extreme drought. Next slide. Yeah, as I mentioned in the previous slide, the 2019 flood immediately preceded a 3-year drought. During this period, AR activity pretty much vanished in our region, which led to significant drop in our reservoir water supplies, causing Lake Sonoma to reach its record low storage, as I mentioned earlier in the presentation. Another significant drought began after a wet start to water year 2013. And December 2012, several ARs caused Lake Mendocino to rise into flood control pool, which forced the U.S. Army Corps of Engineers to release water from the reservoir to bring storage levels down back to near the water supply pool. After the purge of the reservoir, the region then faced the driest calendar year on record for 2013. So as storage dropped in the reservoir over the following year, we began to research whether we would have been able to modify our operational rules to hold on to that water in the flood control pool instead of releasing it as we entered a drought. This event sparked our transition towards forecast-informed reservoir operations, also known as FIRO. Next slide, please.
Nathan, would you be able to explain this hydrograph we're looking at? I know to you it's very second nature, but
sure,
I think that'd be useful.
Absolutely. Yeah, let me go into this a little more in detail. So our green line there, that is water year storage for 2012. And that dashed gray line you see there, that is what differentiates between the water supply pool and the flood control pool. So before FIRO, anytime that storage level reached above that gray dashed line, the Army Corps of Engineers would take over control of the reservoir, and they would have to keep those water levels near that gray line. So in 2012, the green line, all right, so to back up a little bit, at the bottom, we have cumulative rainfall for both 2012 and 2013. They both received about the same amount of rainfall in total, 30 inches of rainfall. The big difference was the timing. In 2013, that timing of rainfall, the majority of it came early in the winter months when the water supply pool is lower. And in 2012, the majority of the rainfall came near in the springtime when the water supply pool would increase, allowing us to store more water in the reservoir. So going back to this water year 2013, got a lot of rainfall in December. It went well above the flood control pool, which is that blue shaded area, and that water had to be evacuated from the reservoir. But then almost immediately after that happened, the rainfall just stopped. No more ARs came in, and we had about 12 months of just insignificant rainfall. So the idea was this water that we see here that got purged, could we have, by looking at forecasts, could we have saved that, modified our rule curve so that we could save some of this water, which would have made all the difference going into a very dry period.
Awesome. Yeah, that's super helpful, Nathan. And it's interesting how the dash line, as you said, the cumulative precipitation is very similar, but then you look at the green and blue actual storage amount, it's 40,000 versus about 70,000. So as you said, the timing is absolutely paramount to inform your decisions. And yeah, very interesting question if forecasts can help make those lines a bit more even, so the timing isn't as big as a factor.
Absolutely. Yep. Okay. So yeah, after that water year 2013, we partnered with Scripps at UC San Diego and the Army Corps of Engineers to modify the reservoir rule curve at Lake Mendocino in order to give the Corps an extra buffer in its flood control pool, which you can see in this hydrograph there. That it's that a light blue shaded area called the FIRO space. So that is a space in the reservoir that was higher than what we saw before. So essentially, once storage enters this FIRO space, the Corps are no longer forced to release that water like they did in December of 2012. Now, if storage were to enter the FIRO space, the Corps can hold on to that water as long as forecasts do not show a significant incoming storm that could increase flooding concerns. So while the drought that began in 2019 was more intense than in 2013, looking at this hydrograph here, this is 2019 storage. That's the black line, that is 2019 storage. And what we saw, so by being able to encroach in that FIRO pool, overall, we saved about 19% more water in Lake Mendocino during that year than if we didn't have that FIRO space. We weren't operating our FIRO operations. yeah, so yeah, unless you got a further question about this slide, I think we go on to the next one.
Yeah, maybe are you able to like put into a tangible statistic? Like what does that extra 20% do? Like how many houses or how long does that last people in Sonoma?
Well, yeah, that's where you get it gets complicated because as storage values change in the reservoir, so does our in-stream flow requirements. It also, as far as water rights users. But I mean, this was the beginning of an extreme drought where ultimately we still felt a lot of pain towards the end of the drought. There's major reductions in water usage. But the point is, if we didn't have that additional 19%, a terrible situation could have been astronomically worse, just much worse. With risk of reservoir crashing and things like that. So, yeah, just having that extra 20% buffer really made all the difference. And like I said, this drought was worse than the one that we experienced and starting in water year 2013, but we were able to weather it, no pun intended, much more efficiently, I would say.
Great. Yeah, thanks, Nathan. Um, nice. I'm going to talk a little bit about HydroForecast, the product that Upstream Tech has created. It's a hydrology forecast, and we have two types of forecasts. One's a short-term forecast, and so this is more for what we're talking about right now. We're in the next 10 days, next couple of days, what's coming my way, and how is that going to impact some of the operations of whatever asset I own in a water body. So for Nathan, for example, dams, but we also have people using it for flood warnings or for mining purposes or transportation. So really anything where having some insight on what will be happening along a river in the next 10 days, that product's really well suited for. We also have a seasonal forecast, which looks several months up to a year in advance. So that's kind of getting to Nathan's earlier point of understanding what's going to be occurring in the next couple months to help inform the decisions you're making right now. And HydroForecast is a unique product and is fun to nerd out over because it came out of some really interesting academic research about 10 years ago about applying neural networks to hydrology to solve this really challenging but important hydrological problem of stream flow forecasting. And so the way the model works at a very high level is it's taking in available hydrological data such as precipitation and temperature forecasts. It also uses data from satellite observations such as snowpack or snow water equivalent and NDVI, vegetation rigor. And it's able to look at hundreds of basins and understand the underlying relationships that are determining how a stream flow is going to respond given the upstream physical and dynamic components. And our company has been producing this forecast for nearly 10 years. And a couple of years ago, we entered into this competition, whereas a bunch of different hydrology forecasts competing head to head. And we're really proud to outcompete a majority of the models in different regions with different statistics. So all around well proven and highly ethical or highly I forget. It's a well proven product that works pretty well. So to round out the webinar, I'm going to talk a little bit about HydroForecast, the short-term model in action in Sonoma a little under a year ago in November of 2024. So there was a pretty significant atmospheric river that hit Sonoma County, and about 13 inches of rain dropped in a little under a week. And this was classified as a 1,000-year event in Santa Rosa. So very extreme, very rare. And about $2 million in damage were reported. So one of those earlier stats that Nathan said that Sonoma County has actually experienced the most amount of flood-related damage in the past 40 years in any Western county, including San Francisco and LA and these really populated counties. And it's because they're getting so many atmospheric rivers. And there's a lot of people and agriculture and lots of uses of all the land. where a lot of this water is getting drained into when these really extreme events occur. And here is a satellite video of the total precipitable water from this event. So you can see the atmospheric river action happening, kind of starting over in the Hawaii area, making that really long, narrow band, and just really focusing on that Northern California area. And this was a unique event because it was actually two meteorological phenomenon happening. There was also a bomb cyclone, which you can see a little bit. So that was a really rapid increase or decrease in pressure. So there's a low pressure cell and there's an atmospheric river. So those two things were kind of working in synergy to suck all of this moisture up into California. And some background on upstream tech in Sonoma. We've been working together for about 3 years now, since 2022. And we provide forecasts for 3 of their reservoirs, Lake Mendocino and Sonoma in the Russian River, and then also Pillsbury, which is in a separate watershed, but there's an aqueduct connecting those two. And we're providing the short-term and seasonal forecast for them. So zooming out of this event, just to kind of put in the scope of how big magnitude it was, this red box I have is the November 2024 event. So it actually wasn't even the highest peak flow at Lake Mendocino, but it was a bit more extended. So the total volume was actually more than some of those other events, but it's one of the top peak inflow events in the past 4 years or 5 years during the winter in Sonoma. So this is what is happening under our dashboard. So if Nathan or one of his colleagues are looking at HydroForecasts before an atmospheric river, this is the view that they're going to be looking at. So on the top plot, we have our inflow hydrograph, and on the bottom, we have our precipitation forecast. And as I said earlier, we're also looking at temperature, snowpack, and NDVI. I just didn't include those just for simplicity. And then one thing you'll notice is there's a bunch of different colors and bands and lines. So since hydrology is inherently a very uncertain subject and all the forecasts we're taking in, they also agree and disagree. The HydroForecast model outputs a probabilistic estimate. So this dark blue line is our mean, which we recommend users use. It's the most probable thing to happen. But there's also 50 and 90% confidence interval, which says there is a 50% or 90% chance that the flow ends up in one of these bands as well. There is also a NOAA River Forecast Center model at this point as well. So that's that red dotted line. And then the observed is kind of this darker line. So you can see that it's a double event. And obviously when this forecast was made, the observed data wasn't available yet. So that's just there to kind of compare what happened and what was predicted to happen. So this is 3 days ahead of the first event. And so all the models that HydroForecast is using are predicting pretty serious rain, about 8 to 12 inches in total. However, there is variation. 8 versus 12 inches does make a big difference for someone like Nathan to understand, do I want to hold on to the water in my reservoir? Do I want to start releasing it to make space for the future water coming in? So this variation is quite critical, and understanding those nuances and how that impacts the specific reservoir and all the assets under management is very critical. Jumping forward about 48 hours, so a little over 1 day ahead of the first peak, you can see that there is a second burst of precipitation. It's kind of tough to see in this view, but the slope is just increasing a little bit. And so the HydroForecast model is starting to see that there's going to be one dump and then a bit of a lull and then a second dump. And so it's starting to take shape of this double peaked hydrograph. And the RFC is still predicting on the lower edge of that 90% confidence interval. Less than 1 day ahead the hydro forecast is starting to see a bit more of overlap and agreement between the precipitation forecasts. So these confidence intervals are decreasing, and that mean is starting to really approach what was actually observed. And the hydro forecast model is updating every 2 hours. I'm showing them at about every 12 or 24 hours. But as all the precipitation forecasts are updating, the hydrology model is reflecting those changes and trying to stay up to date with the latest forecasts. 12 hours ahead of the first peak, the RFC jumps up. It starts seeing some of that rain actually land on the ground and being observed. And it starts picking up the forecasted precipitation. And so its forecasts are rising and approaching what HydroForecast is also predicting. And again, the confidence interval is continuing to shrink as the actual event is getting closer and closer because the uncertainty of the precipitation forecasts are decreasing. And then after the first peak, you can see that the second peak is happening where there's a very dramatic increase or forecasted amount of precipitation, a bit smaller than the first burst, but still after the soil is wetted, the ability for the ground to absorb it is a lot less. And so the models are able to learn that antecedent condition and know that the smaller amount of precipitation is going to actually cause a non-trivial amount of inflow increase. And then the models, they both peter out with the event. And before I hand it off to Nathan to kind of talk a little bit about his experience during this event, which is really interesting, I just wanted to highlight that the HydroForecast model was able to accurately predict the peak flow about a day in advance. In addition to the forecast element, all the information that HydroForecast is pulling together is usually disparate, and you need dozens of tabs open and potentially some custom scripts or API calls to have all that information in a digestible way. HydroForecast gets all that information in one place. So you just go to one dashboard and you're able to look at and investigate all the critical components. And the HydroForecast forecast was about 40% more accurate than what the RFC was producing during this event. And yeah, Nathan, can I pass it over to you to talk a little bit about your experience and takeaways during this event?
Yeah, sure. Yeah, during this, this is the first big major event of the water year, combined with the cyclone bomb. And whenever winter rolls around, I typically just have a whole bunch of tabs open on my browser forecast tools, including the HydroForecast. And and the forecasts are really showing this storm to be about to be a big one. Some of the things we were seeing is that one. Lake Mendocino was in a very healthy place going into this water year. A lot of that to do with forecast-informed reservoir operations, where we've been retaining more and more water each water year. And so it's clear that this storm was most likely going to push storage in Lake Mendocino over into the flood control pool, well, the FIRO pool. And so at which point, operations of the reservoir would then be transferred to the U.S. Army Corps of Engineers. So we made steps in that direction. But in addition to that, Sonoma Water, we are also responsible for managing a flood forecast hotline on the Russian River. We've been doing this for decades. There are several folks all along the river who do not have easy access to the internet or quickly available flood forecast information, who are very susceptible to flooding. So we operate a hotline, and we update those hotlines all throughout a flooding event. So getting a nice heads up that this event was going to produce flooding allowed us to assemble our team, that because we have to be rotating on shifts because it's a 24-hour hotline all throughout the night, and make sure that hotline was up and running. And then we also we have a lot of equipment all along the river. Not just for one, we have a wastewater treatment plant that often gets flooded during big flooding events, and so it's difficult for people to get in and out of the wastewater treatment plant that still needs to be operational during the event. And so we get those kinds of heads up on that, especially for this storm. We get to start making logistical decisions to make sure that the operators at these plants have everything they need in order to keep that plant running properly. And we also had we were doing pretty extensive study out of our collector systems, and so we had to scramble to get equipment out, get equipment in order to continue the study. And then lastly, we have a rubber dam that we put up at our collection facilities. We use the rubber dam during the when water levels are lower in order to do this, because we saturate the area and also can transport the water into some infiltration pond, which increases our production during the drier months. Problem is, if flows in the river get too high, those flows will just take the rubber dam out and it will just get set down the river. So having these forecasts are very in advance, very important to us, because especially in this event too, we were able to see these flows are going to exceed the level that the dam could withstand. So so we had a few days to be able to take that dam out and keep it safe. Yeah, that's about covers it.
Amazing. Yeah, thanks, Nathan. Yeah, and if anyone has any questions on his experience or wants more info, please feel free to drop it in the Q&A. Yeah, and with that, that's all we have for the slides. Yeah, let me go over to the Q&A. I think there's a decent amount for you, Nathan, so get ready.
Okay.
Yeah, let's see. There was one question about the FIRO analysis. Can you explain a bit more about how FIRO analysis was undertaken? I believe that was for the hydrograph that you were explaining.
Yes. Well, so yeah, Hunter, would it be possible to go back to that slide?
Yeah. Let's see, this one, I believe.
Yeah, this one right here. So the main thing with FIRO, so the way that the Army Corps of Engineers historically had to operate, yeah, just once again, with this gray dashed line, the water it drops, it drops significantly during the winter months, because that's when you're most concerned about flood control or flooding reasons downriver. So Army Corps of Engineers cannot hold on to water under the old methods of prior to FIRO if water went up into there. So in December of 2012, they did what they were supposed to do, and they released that water to get it down to the water supply pool. Problem is that they were not permitted to look at what the forecasts were looking out, seeing whether or not is there going to be a ridiculously resilient ridge that is going to build out into the Pacific, which is what in fact happened. And once that ridge happens, the likelihood of ARs coming in just drops off. And so the whole idea is, before releasing that water from the flood control pool, let's give the Army Corps of Engineers the tools in order to look at forecasts. What is on the horizon? Is there already big storms coming in? Great, release that water. If there's not, if it seems very unlikely that anything's going to be causing any flooding onto the river, let's give them an extra tool, an extra buffer room to be able to hold on to that water. And so that's how we've been operating with Lake Mendocino, and we are now in the process of doing the same thing at Lake Sonoma.
Great. Thanks, Nathan. There's another question. Can you elaborate on the 40% more accurate than RFC comment or statement? Was this based on CN RFC deterministic versus HydroForecast media ensemble? Yeah, that's a really good question. And I know there's a million ways to chop and dice up these statements. So we compared the RFC deterministic forecasts versus the HydroForecast mean. So trying to take the deterministic elements out of those two, and the 40% specifically came from KGE King-Gupta efficiency metric, and the mean absolute error MAE was also around 40%. But looking at different stats, the numbers differ a little bit, but yeah, those are two that we usually use. So that's where that 40% comes from. Another question A bit on the technical side, could you explain the model training and validation process as well as the model's performance is evaluated? Yeah, so the training, it takes several hundred basins where the hydrologic properties are known, and also where gauge data is available. And this data set, it's from the Camels data set, if you're familiar with it. It has quite a variety of hydrologic characteristics, of very small flashy basins, the very large snow-driven basins, and lots of things in between. So that's the training data set. And from that, the HydroForecast model is able to understand all these really complicated and subtle relationships and how in certain situations and certain times of the year with certain precipitation forecasts, what the expected hydrological response is going to be. And then for validation, it's kind of a classic machine learning training and testing approach where we give the input and the answer, so to speak, to the machine learning algorithm, to the neural network. And then for the validation, we take away the answer and we have it forecast as it would during operations, and then we compare it to the actual answer. So we do that split of training and testing. And the model, the way we evaluate the HydroForecast model, we have this huge matrix of dozens of different statistics. And so we have some calculations to focus on certain statistics or make a balance so that the most optimal model is chosen from this process. And I should say too that there's two stages of our HydroForecast training. The first stage is our base model, which is using the process I just described of all these different existing data sets. And we're able to forecast at any point using that method. So you don't need gauge data to be able to access that model. If there is a co-located gauge history, we can do like an extra boost or a second round of training to localize the model at that point. So it definitely improves the model, but it's not necessary for the model to be able to accurately forecast stream flow and be useful in operations. For the temporal resolution, HydroForecast updates every 2 hours. I'm not 100% sure for the CNRFC. I believe it's 4 times a day. I don't know, Nathan, if you would have any additional insight on that.
I believe it's 4 times a day. Yes, that's my
Yeah.
recollection.
Nice. And then for the spatial scale, I'm going to stop sharing my screen too. For the spatial scale of the models, that's a good question. I'm not exactly sure like what HUC is used for HydroForecast, but we're using, I believe, 90-meter DEM. So that's kind of like the underlying spatial resolution that is used in that Camels data set. Okay, so the next question, do you have a sense as to whether HydroForecast was more accurate than the CNRFC due to the inclusion of ECMWF forecasts, or is it due to the LSTM model within HydroForecast? Yeah, it's a really good question. I don't know the exact answer. We would have to run some test that really goes into what the model was looking at. But usually, yeah, including more data is usually beneficial. The neural network approach we use is a very data-hungry model. So the more data we're able to provide it, the better time it has to pick up on those patterns. And we've also found the ECMWF forecast to be pretty accurate, even outside of Europe. So I definitely think that would be a big impact. And I do also think that at the core, the different hydrological modeling approach is a huge factor as well. Being able to use those neural networks and rely on the machine learning approach to learn and implement hydrological patterns that are very complicated to be incorporated into the model compared to more traditional hydrological model of figuring out what those are through a more manual approach. I do think there's a lot of benefits to relying on some of those new technologies for that as well. And then does HydroForecast do any post-processing of, sorry, I lost the question. Does HydroForecast do any post-processing of the forecast? We definitely do. These forecasts are really great, but sometimes there are some errors or they'll skip a forecast. So we have a pretty robust post-processing pipeline to make sure that the data quality is what the model is expecting, so nothing gets broken. Let's see. Here's one for you, Nathan. What's something that you wish you knew sooner about managing atmospheric rivers? Do you have any advice that you would like to share to other new water managers?
Yeah, so something to know sooner about managing ARs. Well, so when we're dealing with ARs, what we're most concerned with is intensity, duration, and location. So ARs, as we were talking about, very narrow band. We have a pretty long watershed. And one of the things that we were seeing with this last water year, for instance, is that the majority of the ARs were hitting the southern part of the watershed more than the northern part. So our southernmost portion of the watershed, Lake Sonoma, was getting really the brunt of the inflows versus what was being seen into the northern part of the watershed. So having a better idea of where in the watershed it's going to hit, the timing of the timing, how long each part of the watershed is going to get hit, really gives us a much better idea of what the inflows are going to be at our reservoirs, and also flooding implications.
Awesome. Let's see. Maybe we can do like one more question, Nathan. I know we're running up on time here. Yeah, maybe we can both do this one, Nathan. Let's start with you. Are there any new developments in atmospheric river forecasting field that excites you?
Well, it seems like they're just getting better and better every year. Yeah, I mean, especially down at UC San Diego with Scripps, they are every year they seem to be getting better and better at not only forecasting these ARs, but also other things I really like about it is that they transition into categorizing them, like the strength of the AR, similar to how hurricanes are categorized. And so I think that one of the big things in weather in general is that, yeah, you got all the great data behind everything, but what does this mean to the public? What does this mean to the person that needs, to the emergency responder, to the person that needs to react to this? So saying, hey, we got an extreme AR4 heading in, and it's going to last for 4 hours. That's something that's like, oh, people can understand that. Flooding is going to be expected. Emergency crews need to be ready to go. So yeah, that's the kind of stuff that at least more recently I've been excited about.
Nice.
Yeah, how about you, Hunter?
Yeah, I would agree. There's like a daily bulletin during the winter they publish of all their monitoring stations along the US West Coast, and it has them color coded. And that's something I check every morning. And it's just such an easy way to digest that information. And yeah, something that really excites me, it's a bit nerdy, is that slide I was talking about of all of the developments to understand the internal structure of an atmospheric river. That could be a whole webinar on itself from the folks at CW3E at Scripps, where they're flying airplanes and they're working with the Air Force and dropping radio sondes and other equipment. And that type of stuff is very high tech, very impactful. And the amount of strategy and planning to go into it with multiple agencies, different companies and organizations, and then really understanding where exactly do we want to drop this instrument when we have a certain amount. They're expensive. That whole entire science is fascinating to me, and then feeds into what Nathan was talking about of what is this atmospheric river going to look like? What's the impact going to be? So that's something very exciting to me. And yeah, I think with that, we're going to wrap it. I see there's a couple questions we didn't get to. We will follow up with you all. So we'll send you an email. For everyone, we're going to follow up with a recording of this webinar. So please feel free to check back on it or share it with any people that you think would find it interesting. And we'll also follow up with questions that haven't been answered. And yeah, please feel free to follow up with Nathan or myself if you have any other questions or want to chat more about this. And yeah, we really appreciate everyone coming out and taking time out of your day to learn about atmospheric rivers in Sonoma County. Thank you.
Thank you all.